All right, good evening. It's been about a month since I've last streamed, so I owe an explanation. Um, First of all, it's now, what is it, September 28th? Yeah. So I am definitely not going to be finishing this game in time for the Game Boy Jam. Those are due October 1st, so it's going to be a few days. The game's nowhere near done, so it's just not going to be an entry in the game in the Game Boy competition. That's too bad, but that's fine. Um, Tab over here. So, for the last week, I don't really have any excuse for not streaming. I've been ready for about the past week. I just haven't out of laziness. But prior to that, what I've been doing has been preparing for this stream. So when I began this project, a bit into this project, I started experimenting with Game Boy Advance programming, learning Game Boy Advance programming, and to help me learn Game Boy Advance programming, I started I started developing the same game on the Game Boy Advance in C. And what I wanted to do before beginning this next stream was I wanted to move ahead of the current stage in progress in the Game Boy game in the Game Boy Advance game. I wanted to implement the puzzle mechanics that the game has. And then I wanted to spend some time reviewing the rule set and polishing the logic that makes the puzzles work in order to give myself a strong foundation that I can implement in a pretty straightforward way in the assembly version for Game Boy. So that's what I was doing. So what I'd like to do now is actually demo the Game Boy Advance version in order to give an introduction and an overview of what all the puzzle mechanics are and what we're going to be implementing over the next couple of sessions in Game Boy streams. So let me cut over to the main feed and pull up the, let's close that, and pull up the Game Boy Advance emulator. All right, here's the, all right, yeah, stream looks good. All right, here's the Game Boy Advance game. It is a puzzle game where you move a hero around a field and you have to reach an exit. There are gems. There are gems in the levels, and when two gems of the same shape slide up against each other, they break each other. So the objective of each level is to clear a path to the exit. If you don't match up the gems correctly, you can get yourself stuck in a level and have to restart it. Oops, that one was accidental. When you do it correctly, you open up a path to the exit, and then you can leave. The puzzle element is figuring out which gems you need to destroy in order to beat the level. So if I took this right now and just slid it to the left, I've ruined the puzzle because I destroyed a gem I needed to solve. So the way that you solve this level is by pushing this gem up, then this one to the left, and then you can do that and finish off that level. There are some additional mechanics in the game. A teleporter teleports you to a second teleporter when you step on it. These first few levels here are just pretty straightforward introduction. One thing I want to emphasize, because I want to be really detailed about the rules here, because we're going to have to implement every single one of these rules on the Game Boy. Gems cannot be pushed onto teleporters. I'm mashing the down key right now. And gems also cannot be mashed onto the exits. The player can step onto teleporters and the exit, but you can't push gems onto it. So that's a rule that we're going to have to implement. Another rule right here, this is a special type of gem called a star gem. And a star gem is a gem like any other gem, except when a star gem comes in contact with another gem, it will break it no matter what the gem type is. A star gem can destroy any gem. So the puzzle mechanic for star gems is figuring out which gem to use to destroy it. And then the third mechanic, the third unique level gimmick mechanic is the switches and barriers. So if you step on a switch, a barrier will lower, and when the barrier is raised, you can't pass through it. And if you push a gem on it, it will also lower the barrier. When a barrier is lowered, you can push a gem through the gap where the barrier used to be. But again, once a button is uncovered, then the barrier raises again. You need to cover it back up again before you can push anything over it again. Okay. And then one final twist on the barrier is that if you put a gem, let me restart this level. Take note of where the barrier is. And then I'm going to cover up the button. And then I'm going to push a gem where the barrier was. And then I'm going to uncover the button. If you uncover a button and the barrier is occupied, the barrier won't raise until the barrier has been completely uncovered. So those are the rules of the game. And the Game Boy Advance and Playdate versions have 40 levels in them. Some of them start combining mechanics, like this one has star gems and the button and barrier. This level has no fancy gimmicks at all. It's just that it only has 2 shapes of gems. So it's very difficult to figure out which gems need to be destroyed. So what we are going to be doing is we're going to be implementing all those rules in the Game Boy version. Before we start talking a little bit more, we're going to have a discussion about those rules in just a moment. But before we have the discussion, I also want to just briefly review what we did last stream. Last stream, we got a map conversion script implemented to take levels from the tiled map editor and then convert them into the format that the Game Boy game uses. So if I go here and let's draw like some more open tiles here towards the bottom of the map, and then maybe place another red gem here and a purple gem there, and then save the level. And then I go to the VS Code project and build the game, and then go to SameBoy and reload the ROM. You can see my changes are there. There's something that I did between the streams, which was I ported this, the map conversion script that I made on stream last session. I ported that script to the Game Boy Advance version. And then what I did was I made the script platform neutral so that I can use the same basic script for both the Game Boy and Game Boy Advance version, even though the Game Boy version is written in assembly and the Game Boy Advance version is written in C. And then I also added Playdate support for the map script so that now I'm using the Game Boy Advance map data in the Playdate version of the game. So if I make any changes to a level or make any new levels in the Game Boy Advance version, I can very easily just copy it over to the Playdate version. So the way that I did that is the main script got a lot shorter. And instead what it does is it imports a script that expects to exist in the same folder called make map platform, and that implements the logic that's specific to the one platform that you're working with. So for the Game Boy version, it spits out assembly code, an INC file, and an ASM file. In the Game Boy Advance version, there's a version of this script that spits out C code, and in the Playdate version, there's a version of this script that spits out Lua code. But the makemap.js file is completely identical between all 3 platforms. It expects to import a platform that it can pass some data to. I also added a strings file. Where did I put it? Apps. Strings English.json. which contains some pretty names for each of the different map names, and then they can contain tutorial lines. Right now, the Game Boy version doesn't do. Actually, the Game Boy and Game Boy Advance version don't do anything with the tutorial lines right now, but implemented in the Playdate version, when you go to a level for the first time, if it has any tutorial lines, it'll present text boxes that explain those little tutorials. That's how I teach you how to play the game. So that's what I did between sessions. And that reviews the last session. So I think right now it's time to start getting a little bit more into the weeds with a discussion about the puzzle rules. So in previous streams, above my head there used to be an agenda that would show what I'd be doing on that stream. What is displayed there now, I guess you could kind of think of it as the agenda for the next however many streams. But that is a step-by-step process of how I evaluate a frame or turn in gameplay logic. And to give you a quick preview, I have a couple of other cards that can pop up there where I'm going to be showing and explaining some other concepts of what I'm going to be implementing. So it's not quite strictly an agenda view anymore. It's also going to be some visual aids. So let's talk about how I evaluate a frame. Right now, all that I have is a hero that can move around. He doesn't collide against anything. He doesn't shove any gems. There's a, stepping over an exit doesn't end the level. There's a lot that that doesn't happen, and we need to make things happen. So, there's a specific order that I perform actions in order to make everything play out correctly, and it's listed in that view above. So the first step that I do is if there is an in-flight gem, if you've pushed a gem and it's currently moving, the first thing to do is to move the gem another couple of pixels until it reaches its endpoint. Then after that, if the hero is currently moving, move the current in-flight hero. This is different than starting the hero from moving, from reading input and starting the hero moving. That will happen later. What we're doing at the beginning of the frame is if the hero is currently moving, keep the hero moving. The next thing to do is what I'm calling the post-move actions. This is a set of steps that will happen if that will happen on the frame that the hero finishes moving a single square. So the post-move actions don't happen while the hero is in flight, and it doesn't happen when the hero is just standing idle. It only happens on the exact frame that the hero reaches the end point of a movement step. When that happens, the steps I take is first, break any gems. If 2 gems have matched up, then I need to break them. Second, if the hero has stepped onto a teleporter, I need to teleport him over to the adjacent teleporter. Third, if he stepped onto an exit, I need to begin the level ending process. Fourth, if anything has gone onto the button, then I need to update the button state to indicate that it is now pressed. If anything moved off of the button and is currently uncovered, then I need to update the button state to indicate that's uncovered. And then finally, the barrier. If the barrier is up and the button is down, I need to lower the barrier. And if the barrier is down and the button is up and the barrier is uncovered, I need to raise it. Quite a few checks on that one. And then all that will happen on the frame where the hero finishes movement. The next major step is what I call create the hero intention, which is basically just input handling. So every frame, no matter what, I buffer input. So when moving a character in a grid-based game, in order to keep the controls feeling responsive, what you want to have happen is if the player pushes a direction button while the hero is currently moving, you're not going to interrupt the hero's current movement. Instead, you're going to remember that they pushed that key, and then you're going to execute the movement after the hero arrives at their current destination. So if I'm here and I push up, and while the hero is moving up, I quickly press right, it will remember that I pushed right, wait for me to reach the top, and then start moving right after. So if I go upright, he moves up and then right, even though he was currently moving up when I pressed right. It remembered the right input. It didn't eat the input. It didn't swallow it. It buffered the input. And that helps keep the game feeling responsive. So the first step of hero intention is just buffering the input. I guess that's not actually part of the hero intention, but that's the step at which I buffer inputs. If the hero's state is currently idle, if he's standing, if he's not in flight, then what I'm going to do is actually create the hero intention. And the hero intention is the hero saying, I guess it's the hero saying either I'm going to keep moving, or I'm going to stay idle, or I'm going to attempt to move up, down, left, or right. What was I about to say? Oh, yeah. Okay, so post-move actions, this thing that we did right before hero intention, it happens after the hero finishes moving, and if he arrived at his destination, one of the post-move actions is actually to set the hero state to idle. And then right after that, in create hero intention, if the hero is idle, which happens on the frame that he finishes moving, then we create a new intention that says, I want to move, if there's a buffered input. Okay, next, verify intention. If there's a new intention, if the hero intends to move left, right, up, or down, then a bunch of systems are going to be given the opportunity to block that movement. First, gems can block the movement. So with the hero standing here, the hero would not be able to move left because the gem cannot move left. And so the gem would be given an option. So if I press left, the gem would be given the option to understand that the hero wants to move left, and it will evaluate whether it can move left. It'll see that it cannot, and it will tell the hero that you can't move left, and that will change the intention into a bump action to just play the bump sound effect and not move. If, on the other hand, if I was down here and I pushed up, then I should be able to shove the gem, and the gem can move. And so the gem would allow that hero intention to move through. The map is given an opportunity to block hero intentions because you're not supposed to be able to walk into walls. And then finally, the barrier, which isn't in any of the Game Boy levels right now. The barrier would also be given an opportunity to block hero movement. If the barrier is currently up and the hero wants to walk onto the barrier, then the barrier needs to be able to block an intention. If after all those systems have been given an opportunity to block the hero intention, and none of them blocked the hero intention, and the intention is still to move to another square, then we move a gem if the gem allowed us to move, and it's going to move, and we begin moving the hero if the hero is allowed to move. And that is what we do in a single pass through the game loop in terms of logic. This is only like the logic in a game frame related to the puzzle elements. This isn't related to like updating graphics and things like that. This is only showing like the logical process of evaluating a frame. Okay. So that's what we're going to be doing for the next couple of sessions. And in order to assist this, I want a data structure. And what I'm going to do is, because this is a grid-based puzzle game, I'm going to create a gameplay grid. That's sort of like a logical representation of a game board or something. What I'm going to have is I'm going to have a 2D data structure, a 2D grid data structure where each cell represents one gameplay cell. So like the stairs here are a cell, the gem here is a cell, the open ground here is a cell, the wall here is a cell. I'm going to have 1 byte per cell. And everything that exists in the game except the hero will be represented in those cells. It'll be 1 byte per cell, and I have a particular byte format to represent that. Let's pull that format up now. All right. So the goal of this format is one, to represent what exists at a current square. And for the most part, most of the time, most cells can only have one thing in it. It can be a wall, it can be open ground, it can have a gem, something like that. But there is two complications, the button and the barrier, both of which can have a gem resting on top of them. And so I need a way to represent in the byte format that something is both a button and a gem, or both the barrier and a gem. So it's not as simple as just an ID per byte. And then the second thing that adds a little bit of complication is I want to be able to do certain gameplay logical queries, and I want to be able to do those performantly because this is a Game Boy and it's not the fastest system in the world. So I also wanted the byte format to accommodate certain quick queries to be able to answer some gameplay rules with minimal logic. So the byte format is largely divided in two, the 4 low bits and the 4 high bits. The 4 low bits, 0, 1, 2, and 3, are mostly used to just hold an ID to represent the main type of the cell. And in blue on the bottom, you can see a list of the different tile IDs: empty, wall, exit, teleporter, raised barrier, and the gems. The high 4 bits are used to indicate certain status flags. These status flags are used to help with the button and barrier logic, and they're also used for the fast queries. And then on top of that, in the ID bits, the 4 low bits with the ID bits, bit 3 is a little bit special. Bit 3 is a part of the ID bits, but I specially selected my ID so that every gem has a 1 in bit 3 and every other ID type has a 0. And so even though bit 3 is in one sense is part of the ID set of bits, bit 3 also itself supports a special query where just testing bit 3 can tell you whether or not there's a gem there. You'll see it's used for both just logic related directly to IDs and logic related to some bit testing. Bit 4 is set when the tile in question is a button. So whether or not there's a gem currently on the button, bit 4 will always be set on the button square. When there is no gem on the button square, the low 4 bits will be 0, indicating the empty tile. When there's a gem resting on the button, bit 4 will still be set, but the ID bits will be set to the bits of whatever gem is currently resting on the button. Bit 5 is a lowered barrier, so the barrier is complicated. The barrier is complicated and weird, so you'll notice there's two things about the barrier. Bit 5 indicates a lowered barrier, and then ID 4 represents a raised barrier. So why did I do this? A lot of the basic collision checks will work by just checking if, the collision checks for gems themselves will use to check the ID bits, and if the ID bits are non-zero, you can't push a gem on there. And so I wanted the raised barrier to be represented using ID so that check will, so that the gem shoving check will catch a raised barrier because you can't push a gem onto a raised barrier. Once the barrier lowers, you should be able to push a gem onto it, but I need to understand still that it was a barrier, and so that's where bit 5 comes. So when the barrier lowers, the ID bits switch to 0, and then bit 5 will be set. If you push a gem onto it, bit 5 will remain set, and then the ID of the gem will be set in the low bits. And then if you push the gem off, the low bits switch back to empty, and then if the barrier raises back up again, bit 5 will turn off, and the ID for the raised barrier will be set in the low 4 bits. And then finally, bit 6 indicates either an exit or a teleporter. At first glance, this looks redundant, and it is, because there are IDs for both exit and teleporter. So why is there a bit also for exit and teleporter? That's just a performance optimization for the hero. So the hero, so I mentioned while I was giving the demo of the Game Boy Advance version that the gems cannot be pushed onto the exit or the barrier. And so they check against the ID bits to see if they're non-zero, to see if it can push on. The hero generally cannot step onto any of any not. The hero generally cannot step onto a square if its ID bits are zero or non-zero, except if the destination is either an exit or teleporter. And so I have the exit teleporter bit there, which will just present a single little shortcut for the hero check, where the hero can just check bit 6, and if bit 6 is set, then the hero can go ahead and walk onto that square. And then bit 7 isn't used for anything. Now, right now, I'm not planning any additional mechanics in the game. Everything that I show in the Game Boy Advance version is just how the puzzle works. So this byte representation can fully represent everything that I need in order to evaluate the rules of this game. If I added any additional rules, I might be able to make them work inside this existing format by just adding to it. Bit 7 is currently unused, and so it might be possible for me to start using bit 7 to implement an additional rule. And then additionally, there's a bunch of IDs that are not currently used that I could start using. So without bit 3 being set, I could use IDs 5, 6, and 7 to represent a solid object that's not a gem. And then I could also use bytes, or I could also use IDs D, E, and F to represent new types of gems. So there's space where I could add additional game rules in this byte format by just expanding it. But if I wanted to do something that couldn't be represented in byte format, I'd have to make changes to the byte format and like overhaul it, and that would be annoying. But I'm not planning to add any additional rules to the puzzle game, so I expect that this is going to work out fine. To give some examples for how this byte format will work, I have a couple of queries, a couple of examples of queries. So gem breaking. So when a gem finishes moving, it needs to check its neighbors to see if they are a matching gem type, and if so, it needs to break all the gems in question. So the way that I run that query is for each target byte, if the ID bits are the same as the moving gems bits, or either gem ID is the ID of the star gem, then that's a match and you need to break the gems. To be able to move a gem onto a target square, that is only possible if the ID of the target square is 0. So let's move back to this view. For the ID values, 0 represents empty, so you can push a gem onto that. And then walls, exits, teleporters, raised barriers, and the other gem types, gems cannot be pushed onto any of those. So that query, a gem can move onto a target square only if the ID bits are 0. That's how that works. And then for the hero to move onto a target, it's a little bit more complicated. If bit 3 of the target is set, which again is the gem bit, then the target square that the hero wants to move onto currently holds a gem, and the hero can move if and only if the gem can move to its target, which we just showed in the rule above it. Otherwise, the hero can move to the square to the target if bit 6 is set, which again indicates that it's either an X or a teleporter. If that bit is set, then the hero can move there. Otherwise, if the ID bits are all 0, then it's an empty square, then the hero can move to that square. Otherwise, the hero can't move. So that is how we will use the byte data structure to implement the queries for the game rules. Okay, we're 30 minutes in. I've done an awful lot of explaining. I think we're about to the point where we can start writing code. Or close to it. So what's next? Let's get rid of these right now. Let's pull up this. So what we're going to do, actually, let's pull up this. Let's take a look at the hero code right now. I guess the outline view isn't going to be helpful for me. How do I get rid of the outline? Oh, right, I can do this. Yeah, okay. All right. So with all that out of the way, there's a couple of hero variables. These are all... So what I implemented previously in order to implement hero movement was I implemented pixel-based movement and a hero X and Y coordinate that existed in pixel space. I think I'm going to continue to have all of that, but because the gameplay map is a 2D grid that's based on tiles, I'm also going to need tile space values. And I was thinking of getting rid of basically these pixel space coordinates and instead making its the hero's pixel space position a derived value from its grid-based position plus some offset. I think instead what I'm going to do is I'm going to keep all of the variables and logic here that I already have, and I'm just going to add the grid-based hero coordinates on top of that. The hero won't actually use those coordinates for... Well, the hero will use it for logical queries, but what I learned from the Game Boy Advance version when I was implementing is the grid-based hero coordinates are actually used for quite a few rules. So I want to have those in addition to the pixel space coordinate. So actually, before we implement the gameplay grid, let's actually implement those coordinates. So I'm going to add a couple of variables. Now these are going to be public variables, so actually, okay, so this is a habit that I have from other languages, but I like putting my public declarations below the private declarations. And a thing that I'm going to use this convention when I'm referring to the grid space locations is I'm going to use coord for coordinate. There's probably more descriptive ways that I could use this, but this is just something I started doing in the Game Boy Advance version, so I'm just going to carry it over here. So hero X is a pixel space coordinate, and hero X coord is a grid space coordinate. And then another convention that I have from programming Swift that I've carried over into my Game Boy assembly is my private declarations have underscores prefixed to them. The public declarations do not. Okay, so we've declared two new variables. Those are going to be public. And other things are going to be able to read them. They shouldn't write to them, though. Only the hero should write to these. Okay. Well, it's going to be easy to set them correctly in hero spawn because we've got those coordinates as arguments. So can I do... Okay, I have to load into A. Load A... Where are we loading? We're loading D into A, and then we're going to load hero X coord A. And same thing for hero Y coord. Okay. All right, so when the hero spawns, the hero is going to set the hero's initial coordinates just based off of the arguments that were passed to the function. I could actually I'm not gonna. I could actually optimize things a little bit by I could do this and then swap A and then load here. But I'm not gonna. It'd be a nice little optimization, but whatever. Okay, so transition to idle state. So this is the point where I would want to update the hero X coordinate and Y coordinate. I think what I'm going to do is I'm going to create some new private variables for hero target X coord and hero target Y coord. Game Boy is 8 kilobytes of RAM. I've got so much memory to burn. I don't need to put too much thought on this. What I'm going to do is when I begin moving, I'm going to assign these variables. And then once the movement step is done, I'll just copy them to the public variables. So since I already know where that's going to go, transition to idle state. Okay, that was easy. All right, so then finally what we've got to do is we've got to set the target X coord and target Y coord. So if there's no buffered input, there's a transition moving state, reset step bars, set target. Clear out buffer direction. Again, there's probably a more efficient way that I could do this, but I'm going to do it the easy way. Load a hero Y coord. Oh, the public variable. Whoops. The public variable. Hero Y coord. We're going to be moving down, so that's going to be an increment. And then load target Y coord A. Should really be documenting this big code block more than this. Yeah. All right, so then up. Okay, right. And left. And that should be it for the hero X coordinate and the hero Y coordinate. Let's check. Is it just the constant? It is just the constant. Okay. All right, what's the keys to this again? There's What was it? What was it? Isn't there pause and continue? Continue, finish. Oh, just Command P. Well, how do I get that to... Because isn't this supposed to show up there? How do I do that? Or I can just do C to continue. Okay, program is running. Wait, was it break? No. Oh, stop? Is stop command? Stop. Break. How do I do this? Pause. Examine disassemble help, print, list, unwatch, watch, delete, breakpoint, soft breakpoint, palettes, LCD, wave, ticks, SLD, backtrace, undo, finish. All right. Does this work? Oh. I only want to see one byte. Okay. Can I do... No way I can do this, is there? No. Okay. Actually, is there print? Print. If I do it without the brackets. Yeah, okay. It gives me the address. That's what I expected. If I do print value at, there we go. And then can I do this? No. All right, well. Hero X chord, hero Y chord. Okay. All right, so 6 and 19. If I go up 1, whoops. 18. Those values seem weird. 17. 13. What is going on with those? B and C. Score to 6. 5, 4, 3, 2, 1. See, that's what I expect for the hero X chord. But why is Y chord 13? Did I do something weird when I first set it? Okay, that's correct. Hero Y chord. And then in spawn the hero. E is the map Y. Okay, without any movement. Did I? You know, I'll bet. I think I know where the bug is going to be. I have no idea where the bug is. Did I? I didn't like walk all the way off the bottom of the screen, did I? See, that makes sense. Did I do that? Did I walk all the way off the screen when I last did the demo? Let's walk around all crazy like here for a little bit. No, see, it just got really weird. Okay. All right, there's definitely something going on wrong here. Wait, do we have red? Red? Red and red. Okay. Load hero X chord into A, decrement, put it into target X chord. Load X chord into A, increment, and put into target X chord. Hero Y chord, decrement, and put into hero target Y chord. Hero Y chord into A, increment, and put into target Y chord. Okay. Seems correct. All right, so what about the part where... No, it shouldn't make a difference. Okay, here's what's going on. When we finish hero update moving, we're blindly copying whatever's in these two values into hero X chord and hero Y chord, regardless of whether we're doing a horizontal movement or vertical movement. But these are only set to a sensible value when you do the appropriate movement for the first time. They're never initialized to a sensible default value. That's what the problem is. So they're just populated with junk, and then we make a movement, and then whichever movement we didn't move in, whatever was currently in there gets copied over blindly. So that's the bug. It's an uninitialized variable bug. BGB would yell at me for this. Same boy doesn't. Okay. All right, hero spawn. So, easy fix. Move around in all spammy directions. So hero X chord and hero Y chord should both be at sensible locations. Okay. Move to the top left. Should be 1, 1. Move to the bottom right. It should be, what is it? Will it be 10, 11, or will it be 9, 10? It's 9, 10. Or 9, 8. 1, 2, 3, 4, 5, 6, 7, 8. Wait, this is the X of 1, right? Oh, no, I know. I was okay. All right, yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. Okay. Go to the top. 1, 2, 3, 4, 5, 6, 7, 8. Okay. All right. So now, that doesn't change anything about how the hero moves about the field, but now we have some very helpful variables that always show where the current authoritative position, the current authoritative grid space logical position of the hero is. And that's going to be used for useful things with the gameplay map. Now it's time to make the gameplay map. And that's going to be a new assembly file. How much RAM am I using? Because I'm going to make a big blob in RAM. It should be fine. Because again, the Game Boy has 8 kilobytes of RAM. And even though I know there's a vertex map in there, but there's so much RAM. I've got RAM to burn for days. Okay, work RAM 0. I think that's the only, yeah, high RAM used. Ooh, well, that's cute. Oh, there's also Shadow IM. But aside from that, okay. I should get more of an intuitive sense of what hex values mean, but let's see here. I am currently using 900 bytes of 8 kilobytes of VRAM. So the slack or not VRAM, of WorkRAM. The slack is 1C6E. This should be about 7 kilobytes, a bit over 7 kilobytes. Yep. I've got 7 kilobytes of room left to burn. I'm going to occupy some of it with the gameplay map. So the gameplay map is going to be 1 byte per square. It needs to hold the entire gameplay space. The gameplay field is 11 by 10. So it's like, this is actually 0, 0. 0, 0 is actually kind of scrolled off screen. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 by 10. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In practice, the hero's not actually going to be able to move to the most extreme squares and kind of scroll a screen like this. He's going to be trapped in the middle by nature of the puzzle design. But the gameplay field itself is 11 by 10. But because the swap instruction is a really handy way, is a really fast way to multiply by 16, the gameplay map is actually going to be 16 by 10 instead of 11 by 10. So that way, to calculate an offset of, just remembered something I'm going to need to check up on. Instead of figuring out the offset by multiplying y by 11, since the gameplay map width is going to be 16, I just need to take the y coordinate, swap it, and then I've multiplied it by 16. And then that's the vertical offset. So it's going to be 16 by 10, and each cell is going to be 1 byte. That is going to be 160 bytes. I've got 7 kilobytes left, and I'm about to take up 160 of them using the gameplay map. So let's go to the source file here. Gonna need main in a bit. Let's add game map.asm. Actually, let's rename it to map game, which is not going to be at all confusing with map.asm, I'm sure. Definitely gonna want that. It's not the best name, but it's going to be clear to me while I'm writing, so I don't care if it's not the most intuitive name ever. Okay, so we're not going to need ROM data for the gameplay map. We're only going to need RAM. So section game map vars. It's just going to be workram 0. We're going to call it game map. Is this the first time I'm using this symbol? It should be, but yeah, it's the first time I'm using this symbol. This is fine. Okay. Okay. Build this, and if I look at the sim file, it should be in there. The map file. Yeah, that's definitely a different number. So 1BCE has now lost 160 bytes. Okay. Let's close that. Map game. All right, so next is going to be specify ROM 0. I'm trying to put my game data in ROM X, my game code in ROM 0. This game is definitely easily going to fit into 32 kilobytes, so there doesn't need to be a huge amount of discipline about my ROM code usage, because I'm not going to be doing banking, but I'm trying to keep my code in ROM 0 and my precompiled data in ROM X. Because like if you look, dat/maps.asm, I'm defining the map data in ROM X. This is where the map files are being kept. But the code is being kept in ROM 0. Is the outline really not? No, the outline totally supports this. That's weird. Okay. It's grabbing way too many symbols, but all right, let's create a function called game map build. Turns nothing. This is going to be public. Oh. Let's do it here. Select your map index here. Yeah, it's declared here. Generate vertex maps. All right, gonna create a convenience routine. All right, how many places do I do select your map index? Doing 2 places. All right, all right, all right. Yeah. My calling convention I'm experimenting with is going to require me to do a push and pop here. This isn't the, yeah, well, it's not going to be that big of a problem. No. Yeah, I'm gonna stick with the original calling convention. For this project, I've been experimenting with a new calling convention where by convention, every function needs to be assumed to destroy any register that's not part of its return set. And so any register whose values you want to preserve, it's the caller's responsibility to preserve them. I'm not really liking that convention. I have ideas for an alternative, but I don't really want to switch midstream. What I'd like to do, what I think might be a better calling convention would be to make, what was it? I think it was to make AF and HL caller preserved, but make BC and DE callee preserved. And I think that would result in fewer redundant pushes and pops. If I were to apply that here, then I would need to preserve BC. But like load map address would need to preserve BC because it changes it here, so it would need to push BC and then pop BC. All right, let me make sure that I'm doing this right. Map list, load selected map index into a shift, calculate HL, and then return. Yeah, okay. All right. So what I've just done. Oh, no, HL is the address of it. Okay, so there's one more step here. So this should appear down here too. Yeah. Okay. Load the map list into HL. Calculate the offset of the gameplay map address. So yes, we found the address of the map in the map list, and then we dereference that pointer to get the address of the gameplay map itself. Okay. That was the ROM address. Okay, so anyway, in order for this routine to apply, to do the new calling convention I'd like to do, I would need to preserve BC in load map address. And then down here, okay, so what I'm going to do is delete all this. Okay, all right. So under the new calling convention, I would not have to preserve DE because it would be call E preserved, so I know that would be safe. However, under the actual calling convention I'm using, I have to assume that every register is destroyed. So I have to assume that calling this destroys DE, but I need that to be 0. So I'm just going to move it down here so that I don't have to preserve it and comply with the calling convention I'm using in this project. Okay, and the other registers, BC is only used temporarily because it's in a call to memset. Oh yeah, after memset, everything's destroyed. So there's no registers that I need to preserve right now. So now I should be able to, so right now nothing should be broken. Let's reload this. Yeah, everything still works. Okay. All right. Let's do the same thing down here. Okay. It's down here. And place initial map objects. Place this with a call. Okay. And then likewise, gonna move DE down there to comply with my calling convention so that I don't have to preserve it. So once again, nothing's broken. All right, so made a convenience function. Now let's get back to map build. Which takes the ROM address as an argument. So okay. So it puts in HL the game map ROM address. And because call memset destroys everything, I don't have any registers I need to preserve. So and this right now just returns. So once again, nothing should break. Okay. So what we have now, see, I'm going to need, there's somewhere here that I have a list of the tile types. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B. Yeah. Actually, I want to load up Nova. 9AB. Okay, and hero is 9. 0, 1, 2, 3. Yeah, I think this is all right. Teleporter, hero, switchbearer. Okay. So this list shows me the map format, what the cells, what the bytes mean in the ROM map format. Now the thing is, the ROM map format actually doesn't map one-to-one with my tile IDs. So I'm going to have to go through a bit of a translation layer, but it won't be that bad. In fact, I'm going to go into tiled right now. I'm going to make sure that every tile is represented in the map somewhere, because I need them. Need to make sure they're all correct. Okay. All right, all the objects are in the tile map. So, okay. So in the diagram up there, you can see the different tile IDs I have. 0 is empty, 1 is wall, 2 is exit, etc., etc., etc. But in the ROM format, 0 is empty, 1 is wall, 2 is the exit. But then in the ROM format, 3 is the triangle gem, whereas in the map here, 3 is the teleporter. I was thinking of going to the effort of changing the ROM format to match these tile IDs, and the only one that would get weird, I think, would be the button. And then the hero would also be below the list, but I ended up deciding, yeah, I'm just going to leave the ROM format the same. The ROM format is the IDs in the ROM format are what they have been since the original iPhone game. It's basically just the history carrying forward. But because the ROM IDs don't map to the gameplay tile IDs, that means that I'm going to have to have some code that translates from the ROM IDs to the new gameplay map IDs. So another thing that I want is I want this thing open here. So once we're here in game map build with HL being passed the game map ROM address, it means that HL is currently pointing, like if we're loading the begins map, it's pointing at that byte right there. Now, the thing that I'm observing is that the ROM addresses aren't padded to 16 bytes. It's packed. It's compact, so it should be 11 wide. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yep, it should be 10 tall. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep. Okay, so I'm going to want to iterate over every byte of ROM data, and after every 10th byte, no, after every 11th byte, I'm then going to have to skip. How many bytes is it going to be? Like 5 bytes, 4 or 5 bytes, to jump down to the next row of the gameplay map. In fact, what I think I'm going to do is I'm going to do a blind copy to start, just to make sure that I get the padding right, and then I'll make it fancier. So let's load DE game map. All right, I think what we're going to do is we're going to have B equals row count, and C equals column count. I could do this in one instruction, but I'm going to do it in two. Just for clarity's sake. Okay. Let's see here. So we know that the very final condition, so I'm going to skip all the way to the end of the logic. The very final condition when we're going to break out is if b is equal to 0. Or so we're going to do some work. So b will be equal to 10. We're going to do some work. Then we'll decrement b. And if it's 0, we should... Let's try that. Let's just see what happens. Increment b. Jump relative not z to loop. Otherwise return. Okay. So we need to go through this loop 10 times. So 10... I'm just trying to make sure that I don't hit an off by one error here. Will this loop happen 10 times? I don't think I'm going to get much further than getting the game map built tonight. I think I'm starting to feel my brain beginning to fry. All right, so 10 decrements to 9. Yeah. Oh, okay. So I'll count the passes on my thumbs, and out loud I will say the value of b. So first pass, we decrement b to 9. It's not 0, so we loop. Second pass, 8, loop. Third pass, 7, loop. Fourth. All right, so 9, loop. 8, loop. 7, loop. 6, loop. 5, loop. 4, loop. 3, loop. 2, loop. 1, loop. 0, break. Okay, yeah, that is going to be 10 passes. It's going to make 10 passes through the loop, and then it'll break. Okay. Then the next thing that we're going to do is apply the same logic, which now I'm convinced that this works correctly. We're going to be applying the same logic to C. Jump relative not 0 to loop. So it's going to be a simple copy. Whoops. Simple byte copy. And then what happens when C hits 0? Okay. Can I do increment DE? Yeah, I can do increment DE. It'll take 2 cycles. I just remembered an optimization I want to do. Okay. So we'll have done 11. So I'm going to guess 5. I'm going to guess we want to increment DE 5 times. And I'm going to do this in the most dumb way possible right now. That's 10 cycles. All right. It should do it. Okay, so what we're going to do in the loop is we copy a byte from the ROM map to the game map, and then we increment the byte in the game map. We're going to increment it 11 times. And so I think if we increment it 5 more times, that would mean it would have incremented 16 times total, which should point it to the beginning of the next row, right? So that should be correct. Ooh. I'm going to put this here. No, I'm not. That would be very wrong. But I am going to say it here. All right, and that should do it. Okay, so for 11 steps, what we're going to do is we're going to copy a byte from the ROM map to the game map, and then we're going to increment the pointers to both. After we've done that, we will then increment the game map pointer 5 times, reset the counter variable, decrement the row counter, and if we haven't run out, then we're going to jump all the way back to the loop and repeat everything we just said, otherwise we return. That should do it. Okay. Okay. How many bytes is it showing here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Oh, that's amazing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's very amazing. Okay, so over here, we've obviously got a whole bunch of junk. We've got 5 bytes of junk because we're not actually writing to those bytes in RAM, so they're going to be initialized as random memory. We don't care what they are. We're never going to read them unless we have a bug. We should never read them. But it's kind of fine that they're not 0. And in fact, I shouldn't write to them so that if I play this game in BGB, it will yell at me if I ever try to read them. But otherwise, can I alt? Yeah. All right. This should exactly equal this. Get out of the way. So 1, 1, 1, 1, 1, 1, 1, 4, 1, 1, 1, 5, 6, 0, 7, yep, 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 yep. Down here, bottom row is all ones, 1, 1, 1, 1, 1. So it will be coming from the right, it'll be 1, 1, 1, 1, 3, 0, 0, 0. So 4 ones. 1, 1, 1, 1, 3, 0, 0, 0. Okay. All right, all right, all right. So the naive part is done. It's just doing a naive copy right now. It's not doing the translation to the IDs that I need. But that's a start. All right. Except the thing is, it's not just IDs, it's also bits. So what's going to make sense? So what I'm doing right now is I'm thinking to myself, you know, I have like the rules right here for how I run these queries that says like bit 3, if the target is set, it's a gem. At the part where I say hero move to target, if bit 3 of the target is set, then it's a gem. In the hero movement function, I could write literally that, you know, load up the game map byte, test bit 3. If it's set, then it's a gem, blah, 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 blah. But it would be useful to have predefined constants and macros and things like that. I don't think I'm going to declare any of those right now because, again, my brain is starting to feel a little fried. think I can close that. All right. Okay. How do I want to perform the mapping? I could declare a ROM table. I could declare a ROM table that just maps ROM values to game map values. I would need to push and pop a register to do that. Otherwise, I could have what's effectively a switch table. Switch table wouldn't be fun to write. I'm going to do the ROM table. Okay, so let's look here. 0 is the ground, which is empty. So 1 is the wall, which is 1. Okay. 2 is the exit. Here, I'm going to write 1, 2, 3, 4, 5, 6, 7, 8, 9, AB. All right, so exit, triangle gem, diamond gem, square gem, pentagon gem, star gem, teleporter. I feel like I counted wrong. 0. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B. Switch, barrier. And we're mapping from ROM values to special ID things. Okay, so the exit will become the exit. The triangle gem will become the new triangle gem. The new diamond gem. Square gem. The new pentagon gem. The new star gem. The teleporter becomes teleporter plus bit 6, because bit 6 has to be set. The hero becomes empty because the hero is not represented in the gameplay map. The switch is the button, so it becomes empty plus bit 4. I even changed some of the names from ROM to gameplay map RAM. I am not consistent at all. Okay. And then the barrier becomes the raised barrier ID. It doesn't say. Oh, the exit becomes exit plus bit 6. Let me tab these over. Boy, these the values I'm going to put here are going to be magic values. Like, I should definitely be using like the preprocessor to like bitwise OR an ID with a declared constant for these special bits. But so the exit ID is 2. And then I'm also setting bit 6. Oh, let's get this on screen. So, this is bit 6. So it's 0x42. I want my constants. I'm going to declare the constants. I don't like having those magic numbers. Okay. I think it's NC. Bit and that's here. Yeah, I'm going to truncate this a bit. And then, wait, that's 4. And then I'm going to do a bit for gems because that's going to be used in queries. Okay. It's going to be a new prefix, but wall, exit, teleporter, raised, triangle, diamond, square, pentagon, star. Wall, exit, teleporter, raised barrier, triangle, gem, diamond, gem. Square gem. Pentagon gem. Star gem. Wall is 1. Exit is 2. Teleporter is 3. Raised barrier is 4. Triangle gem is 8. Diamond gem is 9. Square gem is A. Pentagon gem is B. Star gem is C. Okay, so empty is 0, wall is 1, exit is 2, teleporter is 3, raised barrier is 4, triangle gem is 8, diamond gem is 9, square gem is A, pentagon gem is B, star gem is C. Then the bits, the gem is bit 3, the button is bit 4, the lowered barrier is bit 5, the exit teleporter is bit 6, and then bit 7 is unused. Then the flag versions of the bits is gem, button, lowered barrier, and exit teleporter. Okay, those are my constants. All right. Equals ID empty. ID wall. ID exit bitwise OR with the flag version of exit. That's val syntax, right? Yeah, yep, okay. So this is a lot more descriptive than a magic number. It's the ID of the exit, bitwise ORed with the bit for the exit slash teleporter. Is there a way that this fully validates? No, I don't know. Okay. ID triangle gem. ID diamond gem. ID, whoops. ID square gem. ID pentagon gem. ID star gem. ID teleporter. Bitwise OR with flag exit teleporter. This is ID empty. And this is ID empty bitwise with bit 4, and bit 4 is the button. Or no, the flag button. All right, and then this is just ID raised barrier. So flag GM button, we're using exit teleporter twice. Gem we don't have to worry about because that says part of the ID, and lowered barrier we don't have to worry about because the barrier always starts raised. Okay. So how do I want to represent this mess now? I think I'm only going to start with I think I'm only going to show the ROM values. Wall maps to wall. Exit maps to exit plus bit 6, which is exit teleporter. Triangle gem maps to triangle gem. Diamond gem maps to diamond gem. Square gem maps to square gem. Pentagon gem maps to pentagon gem. Star gem maps to star gem. Oops. Teleporter maps to teleporter, bit 6, which is exit teleporter. Hero maps to empty, because hero is not in gameplay map. Switch maps to empty plus bit 4, which is the button. And raised barrier just maps to the raised barrier ID. I could get rid of IDGM empty there because that's just 0 or bitwise and 0 with the flag, but I think this is more descriptive, and when we run the assembler, that's just going to, compile down to the right byte anyway. So it's just being more descriptive that way. Okay, we now have a game map ROM map table. So now what we got to do, we're going to load a ROM byte, which is going to be an index into this table. So we need to go to the table, offset it by that index, dereference that value, and then we write that to the gameplay map. Really don't need to worry about performance because this is all happening when the LCD is off, and it shouldn't really be. Okay. So right here we have a naive copy. So right now, all right. Load ROM ID. Map ROM ID to gameplay map ID to gameplay map value, and then write to gameplay map. Okay. So here's what I'm going to do. I think I'm going to overwrite both HL and DE as part of doing this. No, not that. Load HL. I'm going to do the thing I wanted to do. All right, so RGBDS, I need to know some syntax from some align. Whoops, what did I just copy? What did I just click? All right, I don't know. Oh, this is that bump. Okay. While a line is presented in sections, as often as sometimes you instead want a particular piece of data or code in the middle of the section. Okay. Align. All right, so what am I going to do? I'm going to be doing this both for a ROM table here, and then I'm going to do it again with the game map. What I want to do is align those two declarations to 256 byte boundaries. The reason for that is that it means that every address in the address space is 2 bytes. It's a 16-bit address space. And by aligning everything to a 256 byte boundary, we make it so that the low byte is always 0 for the beginning of these things. And that makes it when we calculate offsets into those declarations, we can just put the offset in the low byte. Technically, what we're doing is we're taking the address and we're adding the offset on top of that. But so long as the chunk of memory that we're declaring is under 256 bytes, if it's 256 byte aligned, you don't have to do the addition. You can just take your offset and stick it in the low byte. Because 0 plus some value is whatever that value is. So it's a neat little performance trick. I'm like not caring at all about a lot of opcodes by him, caring about the performance advantage I can get by aligning these declarations. But part of it is not just performance, it also means I have to write less assembly code. So it's kind of continuing the theme of laziness. Comma, align, bracket. And then what is it? Is it going to be 8 to align to 256? place a section at an address whose align least significant bit are at least equal to offset. Okay, so 8 would be the 8 least significant bits are equal to 0. That would be a 256 byte alignment. So yeah, it's align 8. In fact, if I check the map, I should see game map ROM table declared. What is an S10 file? Yeah, starts at 4,000. Because we forced it there. Okay. And so I'm actually going to do the exact same thing with game map, which is going to make it faster when I'm needing to index it for various gameplay logical queries. Okay, so now what was I doing here? In fact, I can now make this a little bit faster by going because I don't need anything with that at all. Yeah, okay. All right. All right, so map ROM ID to gameplay map value. Let's tab over a bit here. In fact, I'm going to do this. There. That makes it a little bit more obvious that this is a block. All right, and then we write that to DE, and then we... All right. So that should be it, right? That should be me populating the game map. And we're coming up on bit shy of 2 hours, so this will be a good place to stop. So we're going to preserve HL. And then with that, we're going to load the game map ROM table, address of the mapped value. So we're taking the ROM ID and we're pushing that now and pushing it. So we've made HL the address of the mapped value using the little trick I talked about just a minute ago. Then we're going to load the address of that value, the mapped value, into A, and then we just have A that we can write to the gameplay map. And then we're going to restore HL. That should do it. So now, one is still 1, 0 is still 0. Okay, let's see here. This is, what is it? This is the diamond gem. Should be 9. Yep. Okay. The square gem becomes A. So I should see A. Yep. Okay. The pentagon gem becomes B. Yep. Star gem becomes C. Yep. Okay. The teleporter becomes a weird value. So let's check here. 43 is what I'm getting from Same Boy for the teleporter. So we're getting the ID 3, the ID 11, which is teleporter. And then we're also setting bit 7. No, we're saying bit 6, which is the exit teleport. So that's correct. So the teleporter is correct. Okay. The button, Same Boy is giving us 10. Which is, or no, it's giving us 1, 0. Is what it's giving us, which is just bit 4 is set. Bit 4 indicates the button. And it's otherwise the ID is blank, which is empty wall, so the button is correct. Okay, and then the barrier, Same Boy is giving us 4, which is the ID of the raised barrier. Okay. The teleporter should be interesting. It is 42. That's the I already had in the calculator, so I'm pretty sure this is just going to be right. So 1, 0 is the ID of the exit, and then bit 6 is set, which is a bit that indicates an exit or teleporter, so that's correct. All right, so last to check is the triangle gem, which should be 8. That's completely the wrong app. Triangle gem right next to it, 8. Okay. Oh, and then the hero should be empty. Yep, 0, 0, 0, 0. Okay. Okay. Yeah, I think that's everything, right? So that's here, like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, 5 unique gem types: square, pentagon, diamond, this triangle, triangle, star. Yeah, okay. Okay. All right. I think we've done it. I think we've got a functional gameplay map now. And with that, oh, I think my upload rate is lagging. Oh no, it cleared up. Okay. Okay. So now we have a functional gameplay map. We've got the hero. We've got the hero making some coordinate values, and we've got the gameplay map written. So I think that is going to be a good stopping point. I think that, yeah. So let's go over here and switch to the main camera feed. All right, so what did we do today? We gave a lot of excuses for not streaming for the past month. We showed an update for the map script. We reviewed what we did last time. We went over the game rules and logic to explain what we're going to be doing over the next couple of sessions. We declared a byte format for a gameplay map. We added hero map coordinates, which will be queried against the gameplay map. And then we created the gameplay map data structure itself, which we're going to begin using in the very next session. I think next session, what I'm going to do is I'm definitely going to add the logic to exit a map so that if you step on this tile, it'll take you to the next tile. And also definitely colliding against walls at the very least. I think I'll do that by doing a kind of contorted version of the proper final hero logic. And that should go very fast, so I'm going to need to come up with something else. It'll probably be gem shoving. Gem shoving is going to be a little bit... I guess I could also implement this teleporter. And I could start implementing the button and barrier. Yeah, I think I could also implement button and barrier. At least some of it. Gem shoving is going to be a pain because right now gems are represented in the background map, and they what's going to happen is when you shove them, I need to erase the tiles in the background map and then spawn a sprite. And then as the gem is moving, I animate that sprite. I show that sprite sliding to the final position. And then once it arrives at the destination position, I erase the sprite and then write the tiles back in the tile map. And it's going to be possible that I'll be updating multiple tiles per frame. So there's going to be logic involved in that. So feel like that's going to be a session on its own. So maybe the next session will be a bit short as I implement like every rule except anything that has to do with gems. I don't know. We'll see. But I think that's going to do it. Thank you very much for watching, and I will see you next time. Bye.